I'm going to talk about computational fluids modeling, and in some of my research, it spans from a wide range of speeds. So that's what we're going to cover. Here's a couple of examples of some, interesting flow calculations on either the nitro statute out in front or some fluid structure interaction, impinging jets, and just a Falcon Heavy impinging on with a plume hitting an aerospace engineering logo. In any case, just a quick overview of my lab. It's a computational fluids and aerodynamics laboratory. It's directed by me. Here's my contact information and website if needed. Just a little bit about myself. I had about 10 years experience as a research faculty at Penn State. Also a couple of years of experience in industry at Bechtel and GE Wind. My education was mostly from Penn State in grad school in aerospace engineering and a bachelor's in mechanical engineering at Northern Arizona University. So some of the teaching that I go through is mostly in fluids and aerodynamics, so both at the undergrad and graduate level. And I would just kind of conclude with some of my research goals, which really aim to advance CFD models. So CFD is a term for computational fluid dynamics, where we use computers to solve fluids problems. And how do you use these in new applications, and specifically with a focus towards advanced or detailed or complex aircraft applications. So in terms of motivators, some of the things that motivate me in teaching are how do you mix complicated mathematics with tying it to key physical concepts. I really enjoy or strive to get students to learn core physical understandings so that they can understand and keep this information well beyond the schools. And I also try to encourage students to learn numerical methods. Sometimes could be a challenge, but that's what I aim for. And again, in terms of research motivation, I know fluid design can be often very complicated and challenging, and it leads to a strong need for these fluid modeling tools. And one thing that I emphasize is that numerical simulation is a much easier approach to do this because you don't have to actually build something. So I'm going to run you through a couple of different examples of where we did this in the past. Here's one shown right here in the top right, which is a helicopter rotor. So this is actually two helicopter rotors counter-rotating. It actually relates to a space exploration vehicle, and we're using it to develop an understanding of some of the complicated features that's going to happen when we're on a different planet. Also, here's in the bottom left, we have some simulation results identifying and visualizing how transmission of pathogens occurs in the context of a church setting. This is all fully instrumented with an HVAC system, and it's able to convey or to predict kind of like higher level detail of how transmission events can occur. And here's just another example of something called cavitation and how it erodes surfaces in the context of a ship. So this is a ship rudder. What you see here is a bunch of damage from cavitation. And here this simulation zooms into the oscillatory cavitation dynamics that leads to very high loads that drives erosion on surfaces. So we basically use these tools to better understand physical interactions and so forth. So what I want to do next is go through three kind of more recent projects. So the first one is essentially a project recently funded by the Air Force Office of Scientific Research. It's prime through BU. It's actually an evolution of the very first proposal I submitted to UCF. So it took a long time, but eventually it got funded in some form. But it's a collaboration, and really the goal here is to understand what happens when you're flying at very high speeds and you run into something that we think is benign, raindrop. And what does that mean when you're flying at 5 to 10 times the speed of sound. So here's kind of the concept of what happens for some hypersonic vehicles. They fly up high into the atmosphere, go to this glide phase, and they're going at very high speeds. And if they encounter a rainstorm, is it going to survive? And one thing, if you just do a very crude analysis, if you look at various sizes of rain, so this is rain size in terms of centimeters as a function of Mach number, and the force, each one of these lines corresponds to the overall force. And you can see if you're flying at Mach 6 and you run into a rain cloud that has raindrops of order 0.3 centimeters, which is realistic, you're literally flying into what feels like a whole bunch of F-150s. It's huge loads that they have to consider. It's actually one reason why they don't shoot off rockets when it rains. It's at these high of speeds, these raindrops are can lead to very high loads. So what we're doing is, on my part, I'm looking at modeling. So here's an example of some of the modeling looking at a raindrop interacting with a shock. Here you see the raindrop, here you see pressure, and this color is Mach number, so it's at Mach 6. And what you see is this reverberation of a pressure wave that goes through the droplet, and when it reflects back, it leads to a very low pressure. So the goal of what we're studying is that low pressure and how it could potentially lead to cavitation. So that's much like boiling, but it's due to dropping the pressure, and understand how that relates to these loading mechanisms. So once we're done with this, we aim to have a lot of high speed, an understanding of the high speed impact loads with rain. So, and we'll also develop new models and be able to, have tools to understand if we could develop hypersonic weapons that are weather resistant. So the next project I want to talk about is a project that we've been going on for about a year now. It's a NASA tech flight. It's in collaboration with IMEC, and it's funded by NASA. I'd say it also has a little bit of additional funds kind of sitting around here, including the Florida High Tech Corridor, as well as the IMC ORC put some funds that are kind of relating into this same emphasis. And the idea here is we're understanding microfluidics and going in microgravity. So kind of the key reason that the NASA originally funded this is this LFI microscope. It's a really small microscope that has a real broad range of field of view that's really ideal for testing on the International Space Station. So some of the underlying things of what we want to do is how do we develop this microscope so we can understand microfluidics and design tests that can go up on the space station. And we're doing this in the context of studying bone health. And this is where Dr. Kothep from College of Medicine comes in. So what we're doing in our group is CFD design and analysis, as well as some experiments all relating to this. And here we have a couple videos showing some of the progress that we're making. Here's a picture of a CT scan, and we're zooming in, and we have models that are actually representing detailed pore locations in the bones. These pores are bones. So what Dr. Kothep's pushing is understanding how pores or flow in the pores in our bones, this very mild flow, leads to shear stresses, which the bone is colored by. And those shear stresses actually drive bone growth and prevent or relate to osteoporosis. So in the context of the flight, our microgravity flight, we're designing microchips with pore-like structures to understand, and we're sending these up into a Blue Origin New Shepard flight later this year to see if we can't identify some of the mechanisms, the underlying mechanisms that lead to astronauts having higher rates of osteoporosis. And we think that could relate later on down to why people on Earth have osteoporosis. So this is kind of a list of some of the things and outcomes that we believe we will get from this. really the main concept here is this is a nice program to drive a lot of preliminary data for larger grants downstream. The last project I want to talk about is one that's just recently funded. It's with the Space Force. What we have here is a collaboration with SAIC and Space Force. Well, actually, SAIC is going to support us. They aren't collaborating with us, but they are providing internships as well as the Air Force to students. So it's kind of an interesting project. One of the Space Force's most recent goals is they want to deliver 100-ton payloads via a rocket on the other side of the Earth. And the reason why they want to use a rocket is they think they could do this in an hour in terms of flight time. So our effort is aiming on what are the other bottlenecks that are going to occur. So if you look at this kind of timeline, this would be the logistical steps. This is overall time for delivery. If it takes an hour to go across the Earth, all of a sudden allocating all your cargo, maybe doing some drop stuff, whether you're using a parachute or hang glider or something, these timeframes are really going to cut into any benefit you get from that flight time. Luis has all his logistical tools. We're going to start interfacing them with understanding how we load the system and pinpoint bottlenecks there, pinpoint bottlenecks in the aerodynamics and in the redistribution. So some of the income or the impacts here, the primary outcome is developing workforce relevant to U.S. Space Force. They're just forming, and that's one thing that they clearly need. We're also going to develop insight into all the logistical aspects to this cargo delivery problem. Just a few slides on kind of some of the collaboration ideas. Space exploration is an area I've been kind of pushing quite a bit lately. Environmental design and atmospheric and meteorological flows, bioengineering flows, and just complex designs and detailed analysis of underlying things that are going on are areas I think I could I think I could potentially help with. On the last note, these are some of the acknowledgments in terms of students working with me. We've been able to get a pretty good and very diverse in terms of fields, team, that's been really driving most of this research. That's pretty much it for me. If there are any questions, I'd be more than happy to answer.